We will discuss the basic concept of colligative properties in this video. So colligative properties are properties of a solution that depends only on the number of solute particles and not on their identity. So we will be discussing three colligative properties. They are vapor pressure lowering, boiling point elevation, and freezing point depression. So the first one, vapor pressure lowering. Let us see what is vapor pressure first. So vapor pressure is nothing but the pressure exerted by a vapor that is in dynamic equilibrium with its liquid. So molecules will be moving back and forth between liquid and vapor phase. When it is in dynamic equilibrium, what pressure is created in the vapor phase, that is called vapor pressure. So what is vapor pressure lowering? Vapor pressure lowering is nothing but the difference in the vapor pressure of the pure solvent and the solution. So here in the pure solvent, we can see more water molecule in the vapor phase, whereas in the solution, we can see less water vapor in the vapor phase. So that will create a difference in the vapor pressure between the pure solvent and the solution. So what is that difference? That is what is called vapor pressure lowering. So a solution that contains a solute that is not easily vaporized will have a lower vapor pressure than the pure solvent. The reason for that one is when we see the molecules here, in the water molecule, we can see all water molecules on the surface, whereas in the solution, we can see some solute particles also on the surface. So that will block the water vapor, the water molecule to vaporize in the vapor phase. So that will reduce the vapor on top of that solution compared to the pure solvent. So that will lower the vapor pressure. So that is what is the lowering in vapor pressure in presence of a non-volatile. That means it is not going to volatile that easily, non-volatile solute. So if we have a solute that dissociate more into more particles, will have more effect on the lowering of vapor pressure. What is that means is, in this example, we can see Ki, potassium iodide, will dissociate into K plus and I minus. And that means we will have two particles here. Two ions are producing, so we will have two particles here. In NaNO3 as well, we will have two particles, Na positive and NO3 minus. And in the case of FeCl3, we can see that one Fe3 plus ion and 3 Cl minus ions. That means we will have 4 ions. That means 4 particles here. So 4 ions will have more effect than 2 ions in lowering the vapor pressure. That's what it means. So in this case, we have 3 ions. So 1 magnesium ion and 2 nitrate ion. So the order will be in lowering the vapor pressure. The C, that is FeCl3, will have more effect in lowering the vapor pressure. And then we will have MgNO3 twice, because the reason is we have 3 particles, 3 ions in that case. And then we can say NaNO3 and potassium iodide. So if there is some other particle which is not going to dissociate at all, it will have least effect. For example, consider these 3 beakers with different solutes. First one has glucose, and the second one has sodium chloride, and the third one has calcium chloride. So we can see that in the case of glucose, we have only 3 particles, whereas in the case of NaCl, we have 6 particles, whereas in the case of calcium chloride, we will have 9 particles. When you count, you can see that. So which one will have highest effect or more effect on lowering the vapor pressure is calcium chloride, because we have more particles in there. So more particles will be on the surface of the liquid that blocks the water molecules to escape into the vapor phase. And now the second one is the boiling point elevation. So what is boiling point? The boiling point of a substance is the temperature at which the vapor pressure of the liquid phase equals to the atmospheric pressure. So whatever the vapor pressure is creating on the top of the liquid, so here is water, and whatever vapor pressure is creating here, when it equals the atmospheric pressure, we call that one as the temperature at which that is equal, we call that one as the boiling point. So what is boiling point elevation? So the difference between the boiling point of the solution and the boiling point of the solvent. So if we have a sodium chloride or any other solute dissolved in that container, and this is the pure solvent, that is water, and I'm closing that container, and if you have same amount of water, and but you are dissolving some salt in it, that is, it can be NaCl or KCl and any other salt. Okay, so the vapor pressure here, what happens, we know when there is a solute in there, the vapor pressure will go down. So what happens is it will take more time to reach to that atmospheric pressure. So that means we had to keep adding heat energy to that to make the vapor pressure equal to the atmospheric pressure. So what it will do, it will increase the boiling point. So what is the difference between the boiling point of the pure solvent and the solution? That is what is called boiling point elevation, and we can express that one by this formula, that is delta TB, what is the change in the boiling point, that equal the boiling point of the solution minus the boiling point of the pure solvent. So how can we find the boiling point of the solution if you know the change and the solvent? So boiling point of the solution equal the boiling point of the solvent, the temperature at which the solvent boils, plus the change in temperature because it is elevated. That means increasing. So always the boiling point we will add to the pure solvent boiling point. The change in boiling point plus the boiling point of the pure solvent will give us the boiling point of the solution. So the magnitude of the boiling point elevation is proportional to the number of solute particles dissolved in the solvent. So let us take the previous example. So in that case, we can see that we have 3 particles here and 6 particles here and 9 particles here. So we already discussed that the vapor pressure will be high when the number of particles are less, and the vapor pressure is going to be less in this case. And we can see that since the boiling point elevation is proportional to the number of particles, the same explanation we can give. Since the vapor pressure is less, it will take more time to reach to that atmospheric pressure. So that means we had to supply heat energy, and that will result in higher boiling point in the case of more particles, because less vapor pressure, so the boiling point will be high. So vapor pressure less, boiling point will be high. That depends on the number of particles in the solution. So in the case of the first beaker, that is when we have glucose, that is only 3 particles, what happened to the vapor pressure? The vapor pressure is very high. So when the vapor pressure is very high, we will have low boiling point in this case, opposite. And the third one is the freezing point depression. So freezing point is the temperature at which a solvent or a liquid state changes to the solid state, right? And what is freezing point depression is the difference in the freezing point between the solution and the pure solvent. So we can express that one like we did it for the boiling point elevation. Delta, that is change in freezing point, equal the freezing point of the solution minus the freezing point of the solvent. Even though it is going down for the solution, we will express the delta TF positive value. Okay, so we will express that one as positive value, but it is going to be negative because the freezing point is going down when you add salt into it. So how can we get the freezing point of the solution? Is freezing point of the solvent minus change in freezing point. So we are always subtracting to get the freezing point of the solution, whereas in the boiling point we are always adding the change in boiling point. So that's what we had to remember. So for the boiling point we had to add, and for the freezing point of the solution, so for these things, freezing point of the solution we have to subtract the change in freezing point. Okay, so that's the difference between these two. When we do the calculations, we can explain that one in the next video. So this is the point you have to remember. Delta TF is the change in temperature of the freezing point, and we usually report that one as a positive number. Okay, so that is the reason. So the freezing point is going down when we add salt on ice. That is why during the winter season, the salt is sprayed on top of ice on the road to reduce the freezing point of that solid ice. So it will melt easily. So why is it lowering the freezing point is because in the solid form, it has more orderly arrangement. So look at ice here. So for the ice, we have intermolecular force of attraction, that is hydrogen bonding in between them. So it has an orderly arrangement, right? So when that salt is added to this ice, what happens is the ions from the salt is taking in between the water molecule. It is taking the place in between the water molecule, breaks the hydrogen bond, that interrupt the orderly arrangement. So what happens? It needs a lower kinetic energy or lower temperature to get more orderly arrangement back into that solid form. So that's what is happening when you add an impurity or a salt into or any other solute particle into ice. So it is lowering the freezing point. Now let us see an example. Say for example, if we have these three ions, and which one will be having more effect on lowering the freezing point. So here we will have two sodium ions and one sulfate ion. So that means we will have three particles. And in this case, we will have one potassium ion, one chloride ion. That means we will have two ions or two particles. In this case, we will have one aluminum ion and we will have three NO3 minus ion. That means we will have 3 plus 1, 4 particles. So 4 particles means more number of particles will have more effect on lowering the freezing point. So it will have lower freezing point and then 3 particles and then 2 particles. So first it will have more effect on lowering the freezing point and then Na2SO4 and then KCl, right? And now let us try to combine all three what we learned in this example, in the same examples. So we have seen that the lowest freezing point is for AlNO3 thrice. So which one will have the lowest boiling point? The lowest boiling point will have KCl because less number of particles here, right? Only two particles. So it will have the lowest boiling point. KCl will have lowest boiling point. Which one will have the highest boiling point? So highest boiling point we will have highest boiling point for more number of particles. So we will have 4 particles here. So highest boiling point you will get when you add AlNO3 thrice in the solvent. And we will have that means when the vapor pressure. So highest boiling point means the boiling point is high means the vapor pressure is going to be very low. And in the case of Na2SO4, it's going to be in between in all cases. So KCl will have very high vapor pressure and very low boiling point.